No, that's too much. I like you guys, but it's a bit much. An entire empty room, we sit.
No, wow. And then the height again. Two people. One second time. I didn't see you.
I don't know sometimes.
Did you sleep in the house today?
I didn't hear and see. Możemy porozmawiać.
What?
Oh. Yeah, we should start a photo. Yeah, so today we have this second talk by Martin, so stochastic wave equations. Just wanted to remind that tomorrow there are two talks by Sarah and by Dirk, just after the lunch, the second talk. Okay, please welcome.
Okay, so this is the second part of the talk, and it's a continuation of the first one. I see a few different faces here, so those who maybe can't just repeat the first talk here short, but I will just show you the plan. So yesterday we spoke about the classical wave equations. So there was such wave equations where you can imagine the model, and you can see what it does. So it was mostly the models where the wave was the state space of U, which represents the solution. It was just a real value. So there was scalar equations, and we could see the amplitude of the wave of the model that we would be studying. There were mostly these models, and today the main concern will be about these modern theoretical physical models. So these equations, we will replace the Euclidean state space, the scalar one, by a Riemannian manifold. So that will be this. So that's the second part. And if you look at the plan, so we spoke most of the time was devoted to blow-up analysis, and we spoke also about global uniqueness and uniqueness, and we stopped here. So that was just just shortly before the end of the first part. So today I will start with temporal regularity of solutions, and then we'll get quickly to the second part, which will be okay. So it's not a half. It's shorter than a half, so the expected time of today's talk would be below 1 hour, I believe. So let me get to a short. What is it? I think we stopped. So let me start with a reminder. I stated a theorem that tells us that if we are studying such equations, so where there's only dependence in the drift of the first part of the solution, not of the derivatives, and we have a function g, a real valued function which also depends only on u, and w is a spatially homogeneous linear process whose spectral measure is finite, and we introduce the cap f function, which is the primitive function to f. And these functions satisfy the primitive function is non-negative. This f, the derivative divided by the primitive, the indefinite integral, tends to 0 if we go to plus or minus infinity. And g squared, the behavior of g squared at infinity is roughly about f, so the growth of f. So it's not 0, but just bounded. So in that case, we can prove existence of solutions to this wave equation, which takes place for each time in the space H1. So that is the Sobolev space of first order. And if you look at the path for each omega, so then the path is weakly continuous in this space. So weakly continuous is in H1, but the solutions are global. And today we'll be interested in cases when these solutions are not only weakly continuous, but when we have the strong convergence. So that means strong continuity of paths. So this part starts here, I believe. Yes. So that is the picture. We saw this picture already yesterday. So I claim that this is not really an example of the solution, but it's possible that what might happen. Let me recall this again. So a nice wave, you see this, goes, so this is the axis for time. So this is what the nice wave looks like, and as we are approaching 0, so the wave's getting worse and worse and uglier. The frequency is getting higher and higher towards 0, and there is also a singularity at this point, so this one tends to infinity. And then suddenly, in one fixed time, the solution is 0 all the way. So there's an example what the derivatives of the solution might look like. So this is an example of a weakly continuous function. So the concern is, of course, does this happen or not? Because the existence theorem tells us that the path might look like this. So we'll look for answers to this problem. And let me recall something what is just weak continuity. So we can imagine it might happen that there is a function phi of t. So t is an argument. So that means that it's an index for functions that take values in L2. So it is a real valued function. A function with indices t that take values in L2 over 1, 0. And you might find such an example of these functions that for each sequence, there is a convergence to 0 in the weak sense. And what is the pathology? The pathology is that phi of tn doesn't converge strongly for any sequence. You can't find any subsequence such that this could hold in the norm. It's also true that for no subsequence, there is no convergence in measure. So again, you can't draw a subsequence such that this would hold. And the least ugliest thing it presents that you can't find any subsequence where you could get convergence at least on some small measure. So any subsequence you draw, you will converge nowhere except for exceptional set, possibly. So that is what the path might look like. That's what we at least might call that it's ugly. And the aim, what we are aiming to, is to have strong convergence, so to prove, in fact, that these weak solutions are, or weakly continuous solutions are strongly continuous solutions. So that would mean that we could have, of course, so if there is a counterexample, what is the positive case? So if phi of t converges to phi strongly, so then, of course, we have weak convergence, convergence in measure, and it shows us if we converge quickly to 0, so then we get really convergence almost surely. So you can see that this is much better than this. So these are the positive results. We assume again that the spectral measure of the Wiener process we consider is finite, and we also assume that there exists a solution that is in H1 and the continuity is just weak. And what happens if the dimension of the spatial dimension is 1 and f and g are just local Lipschitz functions? So in that case, we have that the solution is really strongly continuous. So this is nice. This can't happen that the solutions were really the ugly ones. Let us pass to dimension 2. So in that case, we must assume that f and g are local Lipschitz and there is a polynomial control on the growth of the derivatives. And in that case, we have the same results. So that means if we start with a weakly continuous solution, then the paths are strongly continuous. In case the dimension is 3 or more, so something else may happen, or it's different, the situation is different, we must assume that that the spectral measure has already some small moment. So there is first restriction. But if the growth of P is subcritical in the deterministic case, and in the stochastic case, subcritical for F, and also for G, so then we have the same result. So there can't be any weakly continuous solution. We also saw yesterday that there is something strange happening if the growth is critical. So let us look at this case. So in that case, when P and Q are critical, we get the positive result only if we restrict the class of considered solutions to some smaller class. So this is the homogeneous Bessel space. It's not very important what it is. It just means that the class of considered solution is somehow smaller. So this holds in the PDE case. The same condition is imposed in the stochastic case. There is still a difference between these two cases, although it doesn't appear so, because the PDE people can prove that there exists always a solution of this regularity. This one, there is no proof yet. So again, we may have very nice proof that the zero set has a very nice property. Okay, so this is not complete yet. If we visualize this, so this represents all possible solutions with weakly continuous trajectories. So we consider just the case D 3 or more because D is 1 or 2, so everything coincides. So if the exponents P and Q are subcritical, so in that case, the class of H1 weakly continuous solutions coincides with the class where these solutions are unique, and also where the continuity is in fact strong. So this is what happens if P and Q are subcritical. If we look at the critical case, so then the picture is different. So if this is the class of all solutions, so then the class where uniqueness holds is smaller. Theoretically, it might happen that there are two solutions of low regularity, and they are different. From one initial condition, there might be two solutions. And we also see that there may be a solution which is unique, but still need not be strongly continuous in this case. Theoretically, we don't know if it's really strong, these inclusions are strong or not, or strict, or sharp. Of course, it can't happen that there will be one solution here and two because there's the uniqueness already. So that is the visualization of the problem in the critical case. And that is the end of the first part of the talk. And now we will pass to the Riemannian manifold valued solutions. So that was just for the classical wave equations, and now we'll pass to modern physics. Oh, I'm sorry. I wanted to say maybe a few words why is this so. So why does this happen? In just one slide, in short slide. So this is the formulation of the solution. We see the cosine function and sine function here. So this is the definition we had on the first slide yesterday. And this doesn't remind, there is no apparent that there should be some regularization of the semigroup or the cosine functions or sine functions as we have it in parabolic cases. So the entries should be somehow preserved. So what we have on the right-hand side should be on the left-hand side. But there is a Fourier analysis result quite deep in PDEs that tells us what happens if we replace the L2 theory by Bessel homogeneous spaces theory. In that case, there are some fine estimates on the left-hand side and right-hand side. We see that there is some singularity happening at 0. So if we somehow modify this to stochastic case, so we can prove that the nonlinear growth of f of g somehow turns to a linear growth of these spaces. So what comes to the right-hand side, so these convolutions become somehow more regular in space and in time too. And we may somehow do this. So we start with something on the right-hand side, and we get something better on the left-hand side. But you see that there is equality, so we do this induction again. So we put here something which is already that we know is better. We get something better again on the left-hand side. We do this by induction, and we obtain that, in fact, that there is a better regularity of the solutions. So that tells us that if we start with a weakly continuous solution, we get something better, and from this betterness that I didn't write here implies that the solutions are in fact strongly continuous. And this is what is missing here, the betterness, something which is better, also tells us that these solutions are unique. So that is how we do it in the subcritical case. So we repeat by induction something and showing that the solution is better and better. But this procedure fails if we're in the critical case. So that means that we must impose this additional assumption here. Too far. So, geometric wave equations. Let me start again with a simple model, a simple case. Let us consider the same equation here. It's deterministic equation, but we replace the real values, the scalar case, by some r of n. Doesn't change much, anything. Let us make another reduction. We did this already yesterday. So we will look for solutions to these equations which don't depend on x. So that will simplify this equation to the Newton law. So we imagine this is the acceleration of some particle in r of n, rd, yes, rn, and we know what force it's somehow. So this is the force field, and this is the law. So the acceleration must be equal to the force that is prescribed. So that would be the case if the state space was r of n. So imagine that we are here. So this is a gravity force. We are on mountains, and there is a slope. And we put a skier on the top of the slope. So he should obey the gravity law. He should fall somehow downwards. But he can't do it because there's an obstacle here. That's the slope, and he can't just enter the ground and fall into the center of the earth. So the gravity law somehow is modified. And if we want to study this equation, so this blue thing, the slope is our manifold in this case. I don't know if it's well visible. So if he is here, so he's not really obeying the gravity law, but he's looking at the tangential part of the force. And this happens in each point of the slope. So there is just the tangential projection of the force he's subject to. But it shows up that it's not only sufficient to replace f by its projections, its tangential projections, but we must do the same thing with the second derivative. And that is what will happen even for our PDEs. So instead of this equation, if there is a manifold, so y, we are looking for y, some curve or something which takes place on the manifold and obeys this equation. So on both sides there are just the projection to the tangent space. And this is what appears on the left-hand side. This strange symbol is the covariant derivative. So that is, we don't look at second derivative, so we may consider this as a definition. If there is a second derivative, so we don't look at the second derivative itself, but the projection to the tangent space. If y is moving on this manifold, so then the first derivative is always tangent, so there is no problem for this. But the second derivative need not be in the tangent space. So that's why we introduced this object that we called covariant derivatives. Covariant derivative. There may be different names for this, but let us stick to this. And now we have this PDE here. So let this represent for the moment part of the manifold, the Riemannian manifold. And the equation is posed in such a way that the initial wave is distributed on the manifold. So it is a function u0 of x, which is rd, but the value is on the manifold. And v0, which should be the derivative, the initial derivative, now must be in the tangent space for each of x. So what is really the Riemannian manifold? It's a manifold, so that means there is a set which is compact, Hausdorff. We assume that that it's metrizable, and each point has a neighborhood which is diffeomorphic to some open set in R of n. And the Riemannian, the adjective Riemannian means that on the tangent space that there is some inner product fixed at each point. And there is a theorem due to Nash, very famous theorem, that tells us that we may imagine this structure to be included in some Euclidean space. So really the picture, we may always look at it in such a way that this is piece of the manifold, and this is contained in some R of n, and this, for example, is the tangent space, this point. And that space of all tangent vectors. A typical example, of course, these are curves, surfaces, and level sets. So that means if you have a function and you look at the set where it attains 0, and you assume that the derivative at each such a point has full rank, the matrix, so then you get the Riemannian manifold structure. So for example, typical example that we consider are unitary matrices on dimensions. But we may just imagine that this is a sphere. So that will be our examples. And let us pass to the definition of the wave equation of the manifold. So what we see here is the covariant derivative in time. And instead of Laplacian, there is this sum where the second derivative is replaced by the covariant derivative. So this is first derivative, and this is covariant derivative of the field. And we have also two initial conditions. If this is still strange, so let us look what happens. Or not yet. There is another motivation for this. So why is this equation important? We had it also yesterday. We looked at Lagrange actions, these functions. So imagine that U is a manifold valued function which is at least twice differentiable. And we look at this Lagrangian. So we have again the derivatives here, but in the Minkowski norm. So this is equal to this integrand here. So instead of plus, there is just minus 1. So that is the first thing. And if we look at critical points, so it can be proved again that these critical points satisfy this equation. So that is exactly the wave equation on the manifold. Now there will be, I need to introduce somebody who knows, maybe somebody don't, what the second fundamental form is. So this picture is there is nothing right seen, but this is the quality of the projection. Gamma, so this is a gamma, so we imagine that there is a curve on the manifold, and it's somewhere here. I don't know why it's so badly visible. And I don't know. Is it better?
Yes.
Is it better now?
Yeah, it's a lot better. You can turn them off.
They're off now, yes.
Yeah, that's good. That's good.
Maybe could these be two switches?
These are the biggest problem.
Yeah, you can turn off these.
All of them are turned off.
No, they are not.
Carefully they are. At this moment, I think according to this instruction, everything turned off.
All right, so I hope that at least something is visible.
It's already done.
No.
That is the best thing I can do.
Okay. So if you could see it, so there would be a okay, so there it's, believe me, there is a curve here. You must just believe me. And we assign, so we assume there is a tangent there is a tangent vector assigned to each point of this curve. So if there is the point, so there is an arrow in the tangent space, and it's indexed by t. So these arrows move along the sphere. And we want to differentiate this. So assume that it's differentiable. So this is green. And the derivative is denoted by red, if there is something visible again. And these vectors, it might very well happen that they get off from the tangent space. So of course, this is parallel. What is? Are there? Okay.
Yeah, we can't really see them. It's hard to see.
Okay, so we must use our imagination. So these red arrows may point out of the tangent space. Might very well happen. So of course this is not intrinsic to the manifold. So you see that some more arrows appear. So we project them. So we project them. We use the orthogonal projection to the tangent space of these. So this is the notation I told you before. That is what we call covariant derivative. So these yellow arrows are now projected to the tangent space.
So x bar t is the tangent space of the tangent bundle.
Yes. So this is really a curve in the tangent bundle.
So x bar is in the tangent space of the tangent bundle.
And there is no x bar.
X
Dot. Yes. Dot is just the derivative. And it might happen that it's not in the tangent space. So it may.
You have the connection which allows you to project down.
Of course, we are in Rn. So this is a submanifold.
It is in the tangent space of the tangent bundle.
Yes, that is true, of course.
Right.
Okay, so I just misunderstood your question.
Right. So then I don't understand how can you project it back on the tangent bundle.
No, just imagine a curve on the sphere. There is running uniformly as a principal circle on the sphere. If you look at the derivative of this function,
it's going to be a
it will
vector.
be vector
to the
tangent.
sphere.
Yeah, that will be tangent. If you
Right,
do
so
the
how
second
do you-
derivative,
Right.
that will be there.
Suppose that the sphere is a tangent model, and then you have a vector tangent to the sphere. How do you project that on the sphere?
I project to the tangent space. This is a,
Can discuss it.
But don't you have the connection which goes from the second tangent space to the tangent space?
That's what he wants to
And
introduce.
that's what
I
you want to
think.
do, covariant differentiation.
so if this is the manifold, it's just a circle. And we have a curve running uniformly about it. So at each point, there is the derivative of this, which is gamma dot.
Right.
This is tangent.
Yeah.
This is the tangent space. If you look at the second derivative, so gamma is a curve in R2. In fact, you can look at this in this way. Because this is a circle. The first derivative is tangent, whereas the second derivative is normal. You just do the second differentiation.
Right.
And what I say, then I project this to this space. That will be 0. So that is the projection. You ask me what it is, I give you the answer. This is it. You can't say why or yes. This is what I mean, that I project to the tangent space. This such elementary. It's too elementary that you're surprised, but I'm really elementary on this level. There's nothing else.
Can discuss it.
Okay. And now this is the third vectors that should be black. And it's just the projection of this vector to the normal space. So what we have here is the decomposition of the derivative of x to its tangent part and to its normal part. And what the second fundamental form tells us what the normal part is. So this is a bilinear operator which takes values. So the entries are tangent vectors at point P, and the result is in the normal space. And this second fundamental form, it just serves us to see what this is. If we start with the tangent vector, vectors which are tangent along a curve, so this is the decomposition to the normal part. And this will simplify our case. So let M be a submanifold in Rn and A be this second fundamental form that we just introduced. And we want to, so this is what we, what is the solution to our wave equation on the Riemannian manifold. And we see that all of these four items are equivalent. So U is a solution of the wave equation if and only if the projection of this operator is 0. So that is in fact the definition between these two. The first and the definition of the derivatives and this and the projection. We also see, so if we have this vector whose projection to the tangent space is 0, so that means that this vector must be only in the normal space. So that is again very easy to see the equivalence here. And the third equivalence is just by the definition of the second fundamental form. So we apply to both of these derivatives and we get away this formula. So at the end we see that if we embed the manifold to some Euclidean space, we are looking for any differentiable function U which satisfies this equation and has values on the manifold. So that is the simplification. So what appears here is a second order, it's a wave equation, but with dependence on first derivatives. So that is the complication, one of them, and the second one is the constraint that U must have values on the manifold. And you see this definition is intrinsic, but all these three others require the embedding of the manifold to the ambient space. So they are called extrinsic. An example, so if we take for M a sphere in any space, so then the equation that we had on the previous slide here is rewritten in this form. So that is what wave equation on sphere looks like. It's just a wave equation with dependence, and it's nonlinear dependence on derivatives with the constraint that it's on the sphere. So we look for solution to such equation.
So your second fundamental form depends on the embedding that you're choosing.
On what?
On this embedding that you're choosing?
Yes, exactly.
And what happens if you change that?
So the equation looks differently.
But the solution should be the same, right?
It should be somewhat invariant for these. You have these. If you start with some embedding, so this is one embedding to some, I don't know, M1, another embedding to M2, and we have, of course, this to be commutative. So the solution should somehow obey this diagram.
That's what your theorem says, basically, that no matter what.
No, it's really, there is one intrinsic definition, which is common to all of them. So a short story, what is known in the deterministic theory. So you see that the theory is not very, doesn't go too far in the history. So the first results appear in the 80s, where people could prove that there is a strong solution, but if only if the special domain is real line. So the dimension is 1, and the manifold may be whichever. So any compact Riemannian manifold, there exists a strong solution. Strong in the sense that it's differentiable, in the sense of distribution, but twice. So the derivatives relate functions. It was generalized for nearly 20 years after to weak solutions. So weak solutions means that it's H1 solution. So there's only first derivatives that exist as functions. The second derivatives are only distributions. It took quite big effort to prove it also in the plane, when the spatial domain was a plane, to get the existence. But there is no more uniqueness of such solutions proven, these wave equations. In higher dimensions, there appeared to be restrictions on the target manifold, which is also necessary. So under this homogeneous space where you may imagine a sphere. So if the target space is a sphere, so you have existence with any dimension of the spatial space. And there are also counterexamples, quite simple. If the spatial domain is 3 or more. So in that case, it can be proven that there are blow-ups constructed very simply, and the higher the dimension is, the less assumptions on these blow-ups for the target manifold appear. So I think if the dimension is 7 or more, so nearly for every target manifold, counterexample of blow-up can be constructed. And similar proofs are available for non-uniqueness of solutions in higher dimensions. So let us look what is done in the stochastic case. So imagine that the spatial domain for us is now one dimension. So the solutions are infinite spheres on some compact manifold. And we look at this equation. So this is just the deterministic part, and we replace 0 by some stochastic perturbation. The noise is again spatially homogeneous, but in this theorem we assume that the covariance function of this Wiener process is at least twice differentiable. So this is stronger assumptions on the regularity of the noise. Of course, you see that space-time-wide noise is excluded in this case. And in that case, we can prove that this equation is only one solution. There exists a global solution, and it's only one. And we also prove that these solutions are independent of the embedding. So there exists one formulation which is intrinsic, one formulation which uses the second fundamental form. Of course, we solve this one in this theorem, and we prove that it's equivalence. So this is known in one dimension. No restrictions on the target manifold. If we still are in one dimension, and M is any target manifold, just Riemannian manifold, and the diffusion has a particular form. So this is just a tangent vector field, G, and G0 and Gi's are linear transformations on the tangent space, each point. So there is linear dependence here on this first derivatives. In that case, we can prove there exists a solution, which is H1, so the less regularity, but we don't have uniqueness here comparing to the deterministic case. And we have less assumptions on the regularity of the noise. So the noise may be rougher. Now we pass to higher dimensions. So the dimension here now is independent of D. There is no restriction on D here, but there is a strong assumption from the manifold. So it must be a homogeneous space. So a compact Riemannian homogeneous space, it's just a Riemannian manifold which is compact, and there exists a compact Lie group of which acts on this manifold by isometries. So this is in fact a couple. M is a Riemannian manifold. This is a compact Lie group, and each element here in this G acts from M to M as an isometry. And also the assumption here is that this is a transient. So each point of M, we can, if P1, P2 are points on M, so there exists a G in G such that G P1 is P2. So we can find an isometry that connects two selected points from one to another. So in this case, this is quite abstract, but this holds if M is, you can imagine a sphere, and this could be just the unitary transformations, the unitary matrices. So that is a compact Lie group. So we see that this result holds if M is a sphere, for instance. So that is existence, no uniqueness. So if we so that's it for what is proven. So that's not much. If we compare the results, so this slide was here before, so that was just the results for the deterministic case. So we have we're on the same level with PDEs on dimension 1. We have existence and uniqueness of strong solutions. Concerning weak solutions in dimension 1, we have existence, but we don't have uniqueness. They have it in deterministic theory. In the plane, we have no result available in the stochastic case yet, at the moment. And if the space is a homogeneous space, we'll be again on the same level. We have proven everything as they did. There are no results on blow-ups on uniqueness in the stochastic case in this moment. Maybe just tell you a few words on how to do it. So the proofs are not very complicated. It should be described what is done. So we solve the equation. We look at solutions of. Let's look at this simple equation. So what we do, we just look at this equation and we try to solve it without the constraint at the moment. We prove that there is a local solution, but we don't know if it's on the manifold yet. So in the second step, we prove that this local solution satisfies this condition. We can do it. And if we already know that this local solution is on the manifold, so then we prove that it's global. It can't be proven in a different way. So it's really, you see that this dependence this is nonlinear dependence, and it could really lead to only local solutions. If we already know that it's on the manifold, so we can use the machinery on this manifold and prove that it's global. In higher dimensions, so that is this result where there's the D case, and we may imagine again a sphere. So in that case, we use a penalization method, and we prove there is a sequence of solutions, just approximated our original equation, and this sequence converges to the solution. But then it's really very important that M has very special and fine properties. So it's just a sphere, for example. So that was the proofs. And that is the picture we started with. So you maybe may now judge also that there is much less known in the stochastic case, and that some chambers are still unopened or closed. So thank you for your attention, and I close this lecture. So that was all that I wanted to communicate to you. Thank you.
So, questions for time and comments?
And so
Is there let's complete the picture on the well-posedness. Is there a continuity in H1 of the initial condition? Whether in the manifold case or in the flat case?
I think so, at least for the strong solution. So that is not in H1 but in H2, because in that case you really have local solutions for free. The nonlinearities are Lipschitz unbounded sets for the equation, and you use the Banach-Fixed point and this local. So there is, I think that it's positive, at least in this case, that there is continuity. Problem could be really if you don't have uniqueness. So in all other cases, we don't have uniqueness, so we don't know really if there is some continuity dependence on the initial conditions or not.
In the non-uniqueness case, did you look at the case where you can look at, take one initial condition and then look at a ray of, like a cone, and then see if that.
I think we don't have it for the methods of proof, so that will require some more attention. Yeah.
Are there results on bounded domains, boundary conditions, and some qualitative results concerning?
I think it's not very important. We did it on RD because PD people do it on RD. But I think if the restriction or if they were interested in bounded domains, so the methods would go without any changes, even on bounded domains.
Yeah, but maybe you can say something on the interaction with the boundary and more qualitative. Not about uniqueness and existence. Okay, this is okay, but some qualitative results of the solutions, evolution of compact supports and this kind of thing.
Well, at this moment, I just can tell you that the proofs of existence could be very likely the same. But again, the answer to your question is that it would require special attention to see if you can really have some quantitative properties when the boundary is there, is present. I think nothing follows just from these methods for free, so that I could give you any answer now.
More questions? I mean, I just wanted to make one comment when I look at Professor Fonaki, that there is some parabolic results, not on wave equation, but on parabolic
Of course.
equation with values in manifolds, which was published by in 1992. But it was, of course, just
Yeah.
for completeness.
Yeah, it's true that parabolic equations in manifolds are studied very well. Longer back to the history, so this is newer. It's not Professor Funaki, of course, but also other people that I didn't mention.
No more questions? So thank you again.